All right, so it's my understanding that we want to talk about using TreeNet in random forest mode for the first part, and then at some point we will switch and cover topics related to using lagged variables in TreeNet as well as other products, because it's the general functionality, right? Okay, cool. So what I will do then, I will I'll do a little bit of talk in the beginning when we talk about random forest in TreeNet, and then we'll do the same thing for the lags. Okay? All right, what you see on the screen here is the SBM 7.0, which is essentially the product that was released this year. And as part of the enhancements that we've added inside of the 7.0 was the ability to run TreeNet in a very special mode, which is essentially emulating a random forest technology. So what I'm going to illustrate here is how one could run TreeNet in essentially building a random forest model underneath. I picked a data set for the sake of this session that relates to the sales of oranges in 10 different stores in Brazil over a number of years at some point in the past. So what I will do here first, when I run SBM, so I'm going to open the data set just the usual way, and I have it in a little extract here called oranges2.csv. So it's a CSV file that has about 3,947 records, 11 variables, 3 character variables, and 8 numeric. Now, the data set itself, let's say if I click on the view data, is organized in a straightforward classical form. So you have a sales date, you have a store ID, and there are overall 10 different stores. Then it shows for each specific day, on date, it shows what is the volume of sales, and obviously that leads to revenue and some other things. Then you also have an indicator whether there was any promotion on that specific day, and followed by month, 1, 2, 3, 4 through 12. Then we have up to 2 years in this data set. Then we also have a weekday, whether it's Monday, Tuesday, Wednesday, Thursday, etc. You also have a sales price that was posted on that specific, basically on oranges on that day in the store. And of course, usually when you have a promotion, that means that the price went down, like from 0.96 to 0.88. Then you have a state. In this case, it's just one of the Brazilian regions. You have a climate, whether it's there are different types of climate. And we also introduced a variable, specifically test50t, that has a characteristic such that all records prior to a certain point in time are part of the learned sample, and once you go at some point into the future for the specific store, then you will see that the test indicator turns to 1. Well, it's not easy to see, but at some point it turns to 1 right here. So it's a very simple data set for illustration purposes. Now notice, and it will become more important in the future, that the data set itself has what we call a time series structure to it. So all the records are ordered along the timeline. For now, I'll just want to model this data set and see whether I can predict sales based on the remaining available predictors. Okay, so I'm going here to the model setup, sort variables in file order. My sales is my target variable, and because it's a continuous variable, it will be a regression. And the modeling engine will be TreeNet, even though very soon we will start building random forest models. Now, as far as the predictors go, well, we're interested in gauging the effect of promotion on our sales. And we may suspect that the month might be relevant. Weekday might be relevant because people have different shopping patterns, different seasons, and different times of week. Price is likely to be important based on the general econometric theory, demand and supply, and things like that, as well as state and climate. So those are 6 predictors that we're planning to use, and because we want to make sure that we build a model that does not cross-contaminate on the time scale, we will use a specifically created test 50 variable that that basically divides our data set into learn and test pieces such that the learn sample comes at an earlier point of time than the test sample. And this is done by each store. Okay, that's it. The next part is a traditional modeling setup. So in TreeNet, I'll run, just for starters, 206 node trees, least squares model using learn rate of 0.1. Now, I'm going to build a single TreeNet model such that we have a point of reference, and later on, once we start building RF models, we can see that things indeed changed quite a bit. So I'm going to hit start. It proceeds by doing the data prep and fairly quickly comes back with this model here. And the few things to notice is that the R squared is 0.537. That's based on the test performance. And then we have this optimal model here. And when I look at the summaries, the usual check is variable importance, see how price, state, month, weekday, promotion. Those are the 5 variables that were identified as important predictors. Now notice that promotion at the very bottom, which is often what happens. You can't really change shopping patterns of people even when you run some powerful promotions. Okay, in any case, at this point, I could go ahead and study this TreeNet model and perhaps modify it and do some other things. But the purpose of this talk is to illustrate random forest. So my next sequence of steps will change TreeNet behavior such that I can trick it into building a random forest model. Again, I go back to model setup, and as you'll see, it really is quite simple. First thing I need to do is switch from least squares loss on the regression loss criterion to random forest loss. At this point, the random forest part of TreeNet assumes a continuous response variable. So if you have a binary response, you can still model it, but you would have to kind of treat it as a continuous variable that happens to have a 0, 1 values. So I switched to random forest here. Now, the next important component will be to increase the number of nodes per tree. See, the default TreeNet models use 6 nodes. In random forest models, I want to increase that number to the largest number possible, or something large but reasonable. Like in my case, I will increase this to 1,000. Now, it doesn't mean that every tree will be developed to 1,000 nodes, because it may always stop earlier when it runs out of records or splits or any other condition, but I want to make sure that that number is large enough. And the number 2, depending on how you model, by default, TreeNet forces at least 10 records in each terminal node. Now, that restriction is no longer required in order to build a successful RF model, and I can easily reduce it down to the extreme, which is having only 1 record per terminal node. So, again, to summarize, I switched to random forest. I increased max number of nodes per tree, and I also reduced individual node size. And the final step and that's where it gets a little, you may forget about it. Random forest, in addition to building very large bootstrapped trees, also introduces a concept of sampling at the node level. And under TN Advanced, we have yet another control here under TreeNet parameters. It's called RF style predictor selection. So if I put a check mark here and change the number 0, meaning that all variables are always tried, but in my case I'll reduce that number of variables to 3. In other words, at each node now I will only be randomly processing 3 randomly selected variables out of the initial available set of 6 or something like that. And typically the recommendation here would be the square root of the number of variables, but you can also play around with the different settings. Okay, so I set the random forest, I increased the tree size, I reduced the node size, and I also activated sampling of predictors here. That's all you need to do. I click Start. It looks and feels as if TreeNet is running, but in reality what it's really building is a random forest model underneath. Now what the results are, first of all, notice R squared in this example went up, so we had 0.537, now it's 0.564. Also notice previously we were building 6 node trees, now we're building 665 node trees on average. And that's because I allowed up to 1,000 node trees, so there was no restriction on tree size, and it simply stopped building those trees when it couldn't make them larger. And as far as the summary goes, everything else looks in a familiar way, like variable importance highlights all 6 variables. And we can gradually look at the plots and see what the actual contribution of all of those variables. So let's say the top variable is price. So when I look at price, the plot here shows that there is a significant increase in the volume of sales when price is below 1.0. And by the way, the price here is in relative terms. Now 1.0 some kind of standard price, and then or average price, and then you go down to those essentially discount levels or added value or increased price, because just sometimes they do that, in different regions. But if you look at the price, clearly you have increased volume as soon as you start hitting discounts of 30 or more %. And if you look at the vertical scale, it's huge. I mean, we're talking about like 1,000 units increase in daily amount of sales. Keep in mind that this is a random forest model, meaning the dependency curves here are obtained by analyzing a random forest model, and this is what kind of makes this run very powerful on both the prediction side, meaning higher R squared, and interpretation side, meaning that we are getting something useful and not just a random forest black box. And just quickly, if you're curious what the impact of other variables will be, what you will see is that the month, for instance, decomposes all individual months into impact either positive or negative. For example, January has associated with the greatest positive contribution to the sales of oranges. But if you look at the vertical scale, unlike price, in thousands, here it's only, we're talking about tens and the most 100 impact. July is the lowest contribution towards sales. And in a similar way, if you look at promotion, clearly we have the fact that there is a promotion running this month. Promotion could either mean that there is some kind of I don't know, discount applied, or there was an ad running on TV, or any coupon in some kind of local newspaper. In any case, the fact that there was a promotion is associated with roughly 80 units increase in the amount of sales compared to non-promotion days. Likewise, climate shows you regions that have the largest sales of oranges, and in this case, on the vertical scale, we're talking about hundreds plus. State has a very profound impact. Well, apparently in Rio de Janeiro state, they have the largest sales of oranges, so that kind of accounts for the state effect. And the weekday also shows some interesting, unusual patterns. For instance, Thursday happens to be the most contributing day to the sale of this product. Well, in any case, this might be interesting to study and to build further models, but the primary goal of this discussion was to illustrate quickly how one can easily build an RF model using TreeNet machinery. Now, it may not look like an RF model in the first glance. It may look like this is just some other version of TreeNet, but as a programmer who developed all of the internal machinery, I can guarantee you that it is an RF model. Why? Because as it builds all of those trees internally, it breaks the connection and residuals, and each tree in this sequence uses the original target, and the end result is always obtained by averaging all of those individual predictions. Okay, great. So let's move on to the second part, right? Okay, so what I'm going to illustrate now is to bring up yet another machinery that's available in 7.0 that will allow us to enhance the understanding of this little oranges example and introduce some elements of autoregressive models and time series. Well, before I go there, let me open the data set again in the table form and emphasize that the way the data itself is structured is a collection of records that are ordered along the timeline and also aggregated by store. So in other words, if I look at the store number 51, whatever it means, the records for that store occur in the data set as a single block. And within this block, they are ordered by time. Also notice I have gaps. Like in January 2008, I have dates 7, 8, 9, 10, 11, 12. And then it jumps to February. 7, 8, 9, 10, 11, 12. Then it jumps to March. Then in some other dates, like in June, you could have the same number, but once you go into, say, August, you get 7, 8, 9, 10, 11, 12, 13, 14, all the way to the 31st. Okay? So the way the data set is structured is you have a block structure, and you have a time structure, and then you have additional block structure within the time, which represents those gaps. Now, how can we easily detect the boundary of those gaps? Well, you can look at the store number, and you can look at the month. As long as you have a break in either store number further down when we move to a different store and or month, as you go from one month to another, we have essentially a lack of contiguity or continuity as far as our timeline goes. Now, that information will be critical for setting up a time series model. And if you ever want to model time series on your end, the first critical step is to ensure that your data set has this time component sort order already in place. I mean, unfortunately, we do not allow yet sorting on the fly or doing all the other things. So the key assumption to run a time series application in SPM is to structure your data such that all the records are ordered in by time within each block, and there is some kind of either single variable or a combination of variables that is used to reflect this block structure. So in my case, the block variables will be store and month, so that I know as long as I have same store and the same month, the resulting records are ordered contiguously in time. Now, once I have a data set structured in this form, then I can introduce the concept of a lag variable. And by the way, it doesn't have to be as complicated as in this example. It could be just one single block of data from first record to the last, and all of the records are ordered by time, and there are no gaps or no additional transitions, and there's only one entity. I mean, that's a lot of time series applications that are like that. But what I'm showing here is that in a real situation, you may run into block structure time series, and that's why you may need to do extra work organizing your data to reflect it. So in any case, what the lag variable that I'm going to introduce here means is that when I build a model for sales, in addition to using these predictors that are available here, I also want to use information from the past point in time as a potential predictor. So for example, let's look at the promotion variable here. This is the promotion at this date, on this specific day. Like say here, there was no promotion on July 27th, 2008. I can introduce a promotion lag 1 that says another variable that communicates whether there was a promotion a day before. And the way lag variable is introduced, and in this case it's called lag 1, is it takes the entire promotion column and essentially shifts it down by one cell, so that the value that was on July 26th now becomes the value on July 27th, and so on and so forth. And at the same time, I have to honor the block structure, which is reflected by store and month. So when month changes from 7 to 8, here I have a gap. So if I want to construct a lag value for August 7th for my promotion, I have no information available from the day before, and this value will therefore be missing in that lag 1. So one way to think about a lag operation is that it takes the column that is being lagged and shifts it down by either 1 or 2 or 3, and that's why I can have lag 1, lag 2, lag 3. And it also adds missing values in those cells where the lag information cannot be recovered due to the block nature of records. You either moved to a different store, or you moved to a different time span, or perhaps you have other more complicated layout in your data set. In the simplest case of having only a single time series, no blocks, no gaps, a lag 1 will only introduce first record as missing value because we don't have information about the day before the first day available in our records. If we have a lag 2, that would introduce missings in the top 2 entries, and so on and so forth. So that's just a little rehash of what lag operation means, just in case it's something strange they have not experienced, used before. So now, having said that, let me show what happens if we do go ahead and add lags into our modeling cycle. So I'm going back to model setup. I'm keeping settings as before. It's still going to be a TreeNet random forest model. I mean, it's a random forest model that is built around TreeNet machinery, so I'm not changing anything there. The only thing I change is I go under LAGS menu, and first I need to communicate whether there is any block information in my data. If you had a time series from first record to the last, no blocks, then you might as well keep this information blank. But in my case, I do know that I have records from different stores, and there are gaps at some monthly level. So if I specify store and month as a block variable, and also ensure that in my data sets, records are essentially grouped together by store and month, and within each block they're also ordered contiguously by time, then I will be fine. And then I will introduce a lag 1 on my sales. That means that I am using sales as predictor here. I mean, sales is a target here, which means the original sales cannot be used as predictor, obviously. But in the lags, I am going to use information about sales from the day before as a potential predictor. Now, this is what we call autoregressive time series, when the response at the given point in time is modeled based on a response at some past point in time, which is a legitimate operation. So presumably, if I know how much I sold today, that can help me to predict how much I'm going to sell tomorrow. And likewise, it might be interesting to know whether there is a promotion today and whether there was a promotion yesterday. Now again, if I go back to model setup, my promotion today is a predictor for the sales today. But under lags, I'm introducing promotion lag 1, which means a variable that communicates whether there was a promotion yesterday. Now, month obviously can't be used as a lag just because, well, I mean, it could, but it would not give us any useful interpretation. Likewise, weekday, because those are all natural. Then we have price, a very useful potential lag. And again, state doesn't change, climate doesn't change, and that's pretty much it. So what I've just introduced here is 3 lag variables. So in addition to available predictors, I'm enhancing my data set with 3 more variables that communicate yesterday values for sales, promotion, and price. And that's all I need to do. Then I click Start. The data prep honored all the block structure, and it added all of those lag variables that I've requested. And once it finalizes my run, it needs to calculate plots and all the other stuff. Okay. Once it finalizes my run, the first thing I see is that my R² went up this point to 0.5936. So I'm actually gaining on the prediction side. And in many cases, people add lags to capture additional informational content. They could care less what those lags actually mean. So they could add first, second, third, fourth, fifth lag, and as long as your model performance improves, that means that you've captured some kind of past information that happens to be useful in modeling your future. And that's one way to think about lags. Another way to think about them is that they, in some cases, do add in your understanding or interpretability of the data. So what happens here is the following. I click on the summary reports, look into variable importance, and notice I have a variable price That's the price today. But I also have a variable price with angular brackets 1. Now that is a lag1 variable that was created in addition to price, and it references price level the day before, while at the same time honoring store and month block information in the data set. Likewise, I have a variable sales, which is my target, but I also have a variable sales lag1, and that's the variable that communicates how much I sold yesterday in that specific store. And in a similar way, we have a variable promotion, which is whether there's a promotion today. And there is also promotion lag1, which communicates whether there was a promotion yesterday. Okay, now notice these lags, they are not the most influential ones. They are towards the bottom of the list, but they did add, about 3 percentage points to the R-squared, which in the case of prediction could be a pretty important and significant enhancement. More interestingly, if I look now at the plots, I can compare what happens with all of those individual variables. Well, first of all, let's look at essentially let's look at the promotion first, just because we know that the promotion is usually associated, hopefully, with increased sales. And we've seen it before, and we see it in the new model, that the promotion one, the fact that we promote our product today, makes a positive impact on our sales today. More interestingly, when you click on promotion yesterday, if you look at this plot, it's inverted. And it's also important to keep an eye on vertical scale, because here the partial dependence goes to about 70 units. So the fact that we're having a promotion, the net effect of promotion on oranges, once we accounted for all of the other variables, is positive 70 units increase in sales. However, if there was a promotion already yesterday, that reduces that impact of promotion itself by about 10 units. So one way to think about it is that when the promotion just started, you have the strongest impact on your sales. But when the promotion persists into the second day, then you basically have a drop of about 15% in your sales, and that's according to the data that we have. And again, it's a kind of interesting example to show how lags can be not only useful for prediction, but also for interpretation. There's another interesting one here, which is price. We know that price is a very important driver, because that's probably the most important contributor in explaining the volume of sales. But notice we also have price 1, which is price from yesterday. And when you look at this plot, it looks a little bit more strange. And if I position it here, it kind of makes it an interesting point to contemplate what is the plot is trying to communicate to us. And here is one way to think about it. Suppose on a specific day there was no promotion and the price was set around the average 1.0. Now suppose from that day going to the next day, we've introduced some type of promotion, which could be as simple as adding a tag on the product saying we have oranges for the 30% discount for sale, or say 50% discount. Well, in this case, the second day price goes down to 0.5, our sales go up by 600. But on the second day, we still know that there was no that the price the day before was in this range, and the positive contribution of that information is about 20 or 30 units. As I keep this reduced price into the yet another day into the future, this variable value will also move into this region, because we're already kind of lagging behind, and the result of that will be that now my positive contribution due to original price on its own will be reduced by about 40 units as the result of lagging effect and the saturation of the initial wave of promotion, something like that. So these problems can be a little bit mind warping, because you kind of need to understand what the data represents in your data set. And once you introduce lags, the right way to interpret them is to think in terms of these time experiments, like what happens as I move in time and certain information is lagging behind. But once you analyze it from that point of view, you'll see that all these plots all of a sudden starting to make sense. And the final thing is, don't forget that we also included sales from yesterday as a predictor. And it turns out that it has this interesting shape. Again, not a very strong contribution, about 60, 70 units altogether. And it looks like the sales from yesterday are extremely critical in this initial segment. And as soon as your sales volume exceeds about 300, there is no other regressive contribution of that variable. Now, most typical classical time series models, they assume other regressive models as essentially a linear model when the past effect enters linearly all across the board. Now, TreeNet has a powerful capability to correct for that, because it only contributes this lagged target for the part of the range where it's really contributional, and then levels it off like that. Okay, so that's an illustration of lag 1. As you may guess, it's fairly straightforward to generalize it to higher lags. So you could say, okay, it looks like promotion and price were informative in terms of going back one day. What if we go back one day and also 2 days? So now I have a new structure on my predictors where I have original predictors here, 6 altogether, and I also have 3 variables as lag 1 and 2 variables as lag 2. And now all I need to do is click Start. All of those shifted time lagging variables will be created for me automatically. They will also honor block structures imposed by stores and months. And once the model comes back, let's see what it shows. Okay, so I have a model here. There's still a slightly better R-squared, so I'm squeezing another maybe a half a point or so, a little bit more. So I'm losing that extra effect, and it often happens in these situations as you go further back in time. The kind of contribution of that diminishes and levels off. But in any case, if I look at the summary variable importance, I do see those lags entering at the bottom. So now I have not just the price today, but I also have price yesterday and price the day before yesterday. And the same goes with promotion today, yesterday, and the day before yesterday. And if I look at my plots, and again, for some researchers and for some modeling tasks, all that matters is that you're getting higher accuracy. You could care less how those variables contribute. But in this example, it's instructive to look at the actual nature of lags. And we've already seen, for instance, that promotion by itself has a positive contribution to sales. Promotion yesterday negatively impacts sales, and promotion the day before yesterday also negatively impacts sales, but not as much. So it's almost as if you have a diminishing effect of that initial wave. When something goes for sale, people immediately start buying it, like the first comers and so on, but that it stays on sale, that initial kind of wave of levels off and even diminishes a little bit. And the same thing happens if you look at the, say, the price level. We know it's the fundamental driver based on all of the economics, but we've also noticed that the price from the day before exhibits this kind of lagging effect, and the price from the day before yesterday is essentially similar lagging effect, but even more pronounced. So it basically says that this is a kind of indirect way to highlight how the fact that something goes on sale today gradually propagates back. So if something went on sale today from 1 unit price to only 40% of the original price, I have a 600 increase in my sale. But tomorrow I keep it at this level, but tomorrow my sales going to drop by about 30 units because I go from here down to here on the lag variable, and I stay there. And the day after tomorrow, again, I'm going from here to here, and I'm losing yet another 20 units. So that kind of illustrates that in this specific sales operation dealing with oranges, the effect of promotion goes like the first wave gives me some significant increase in my sales, but the days that are following there is a reduced sales, but by about within something like 10% of the original impact. And there you go. I used LAGS machinery to essentially capture some interesting dynamic patterns in this specific data set. And the final note here before we go into questions and answers or just general discussion, let me highlight quickly on the syntax of this. Because the thing is, what you put in LAGS, you use here the GUI interface. But there's a very simple underlying command syntax that you can start using bypassing this entire GUI side. So let's go to the command log here and look at how LAGs are introduced at the command line level. And here is this example. Notice the keep statement that supplies the list of predictors, and it lists original predictors here, followed by names of the original predictors and in angular brackets lag1 and lag2. So if I wanted to add lag3, I just add another variable like that, lag4, whatever. And you can also use a shortcut notation. So for example, and just to be more entertaining here, let's highlight this, let's say copy. Then I will open new notepad window. I'm going to paste this. And on the command line, let's say you have a variable promotion. And the promotion, we used lag1 and lag2, including the variable promotion itself. I could have used either listed that variable 3 times, as the way it's done here by the GUI, promotion, promotion 1, and promotion 2. Or, as a shortcut, I could use angular brackets and say, I want to start with the promotion by itself, and lag0 means the variable itself, followed by 2 more lags, which is lag1 and lag2. And this way I can eliminate promotion 1 and promotion 2 from my keep list. And likewise, instead of price 1 and price 2, I could just say price start at 0 followed by lag 1 and lag 2. And the shortcut assumes that the lags are consecutive, so you can't really skip over. Now, if you want to skip over, you would just introduce them as a different variables. And then I can get rid of this price information. And by the way, I could also eliminate some of the original predictors. For instance, I could say instead of price as original plus lag 1 plus lag 2, I could have just used price lag 2, and none of the other variables would enter into the model. So it's quite flexible. And in this case, once you've decided on the exact structure of your keep list, I could say submit window. Now, well, I think I have a theory on that. So I specify it like this, and let's see if it fixes it. Yeah, okay. So instead of comma, you put a dash in there, and hopefully, if we execute TreeNet Go at this point, I should see the same run as before. See if it happens.
Yeah, it does say that it should be a dash, but I think the comma should work. Because what if you wanted to do 30, 60, 90?
Okay, so I got this result, 0.60599. And I have, yep, it's the same identical run as we had before, except it uses a shortcut notation. And so to summarize, in order to run lag variables, the number one most critical thing is to have your data set structured that in a special way that supports the use of block variables and lag variables. And by the way, the block variable is just introduced as block store month. It's a block command. And the lag itself is introduced just as a new variable in the keep statement that modifies the actual lag number. And once you have the data set in that structure, you can introduce as many lags as you like. The software will handle them for you. You'll start seeing them in the outputs. So otherwise, they are treated as if you created a whole new set of variables and added them to your predictor list. The lag machinery is generic, has nothing to do with TreeNet or a ref or anything. So whenever in the command line you see this lags tab, that means that it's available, and pretty much all of the engines should support it, except maybe with some minor quirks in those situations when missing values may cause a problem, because any lag operation naturally introduces unavoidable missingness in all of the lagged variables, and the engine should be able to handle that properly. But most kind of the mainstream engines already support it nicely, and this is something that we keep on enhancing. Very useful technology, relatively straightforward to use. The only caveat is that your data set needs to be structured in a way that supports whatever is it that you're trying to do. And once you do that, everything else becomes nice and easy to interpret.